All right, today we're going to tackle one of the most interesting curveballs in all of trigonometry, the ambiguous triangle. It's one of those things that can feel a little tricky at first, but I promise by the end of this, you'll have the exact tools you need to crack the code every single time.
So picture this. You get a geometry problem. You're given the lengths of two sides and one angle, but it's an angle that isn't tucked between those two sides. It seems pretty straightforward, right? But the real question is, with just those three pieces of info, how many different triangles can you actually build?
And here is where it gets wild. The answer isn't always just one. Sometimes, with the numbers you're given, you can't make a triangle at all, 0. Other times, you get exactly one perfect triangle. But, and this is the crazy part, sometimes you can create two completely different triangles from the exact same starting pieces. That is what we mean by ambiguous.
So this whole situation has a name, the ambiguous case. And it really only pops up in this one specific scenario we call side-side angle, or SSA for short. That's our setup, two sides and an angle that's not between them. When you try to use the law of sines here, well, you can get some pretty surprising results.
So how in the world do you know if you're looking at a 0, 1, or 2 triangle problem? Well, it's not just guesswork. It turns out there's a clear set of rules, kind of like a decoder key, that will tell you the right answer every single time. So, let's break down how to use it.
Okay, this table right here, this is basically your cheat sheet. It all comes down to a couple of key checks. First, if you do your calculation and find that the sine of an angle is greater than 1, stop right there. That's impossible. 0 triangles. No way. Now, if the side opposite your given angle is longer than the other side, you're safe. It's always just one triangle. But the real fun begins when that opposite side is shorter, because that's our signal that 2 triangles might be in play.
So how can you possibly get 2 triangles? Well, try to picture side A as if it's attached by a hinge. It can swing back and forth, kind of like the arm of a compass. If that side is just the right length, it can actually connect with the base at 2 different points, creating 2 totally valid triangles, one that's acute and another that's obtuse.
And okay, when you do run into that 2 triangle situation, how do you find that second angle? It's actually super simple. The key is this one little formula right here. The second possible angle, let's call it B prime, is just 180 degrees minus the first angle you found. That's it. Let's see how that plays out.
All right, theory's great, but let's see this stuff in action. We're going to open up 3 different case files, one for each possibility. No triangle, 1 triangle, and the big one, 2 triangles. Let's put our decoder to the test. First up, the no solution case. So here are our givens. Angle A is 50 degrees. The side opposite it, A, is 5, and the other side, B, is 10. We've got our classic side-side angle setup. Let's see what the law of sines has to say about this. We just set up our ratio from the law of sines to figure out the sine of angle B. We pop in our numbers, that's 10 times the sine of 50 degrees, and we divide the whole thing by 5. When you punch that into a calculator, you get a number around 1.532. And boom, that number, 1.532, that's our big red flag. The sine of any angle in the universe can never ever be greater than 1. It's just not possible. So since our math led us to an impossible answer, our conclusion is simple. You can't build a triangle with these parts. Case closed. Okay, on to our second case. Here we've got angle A at 40 degrees, side A is 15, and side B is 10. Now, before we even touch a calculator, let's go back to our rules. Notice that side A is bigger than side B. That condition tells us right away that we should expect exactly one unique solution.
And look at that, the math confirms it. We used the law of sines to find angle B, which comes out to about 25.4 degrees. Once you have 2 angles, finding the third one is easy, right? Just subtract from 180. Then one last run with the law of sines gets us our final side, C. Just one clean, tidy triangle. No ambiguity here.
And now for the main event, the 2 triangle case. We're given angle A is 30 degrees, side A is 8, and side B is 12. Now, what's the first thing you notice? That side opposite our angle, A, is shorter than the other side, B. This is your signal, your cue, to be on high alert for 2 possible triangles.
So, let's do the math. We calculate the sine of angle B, and it works out to a nice, clean 0.75. Now we run our checklist. Is that number between 0 and 1? Yes, it is. And did we already confirm that A is less than B? Yep. Ding, ding, ding. We've officially got a 2 triangle situation on our hands. So let's find our two different versions of angle B. The first one, B1, is just the inverse sine of 0.75, which gives us about 48.6 degrees. Now for the second one, B2, we use our special formula, 180 minus that first angle. So 180 minus 48.6 gives us 131.4 degrees. Two possible angles for B.
And each of these B angles creates its own, totally separate, unique triangle. From here, we just solve for the rest of the pieces in each case. For triangle 1, we end up with a big angle C and a long side C. But for triangle 2, we get a tiny angle C and a much shorter side C. It's amazing. Two completely valid but very different triangles, all from the same three starting pieces.
Now, it is really easy to make a small mistake with this stuff, I get it. But honestly, almost all of the errors fall into two main traps. If you can just learn to spot these two, you're going to be in fantastic shape.
The number one mistake, by a long shot, is just forgetting. You see that the side opposite the angle is smaller than the other side, and you just solve for one triangle and move on. You've got to train yourself to have a little alarm go off in your head that says, wait, check for two. The other trap is finding that second angle but forgetting to check if it actually works. If your original angle A plus your new B prime is already over 180 degrees, well, there's no room left for a third angle C. So that second triangle is actually impossible.
So you might be sitting there thinking, okay, that's a neat math puzzle, but why does this actually matter? Well, it turns out this whole ambiguity thing isn't just for a pre-calculus class. It has some seriously important implications in the real world, especially in fields that depend on getting precise locations right.
Just think about the GPS on your phone. It works using something called triangulation. It's basically using signals from satellites to do a whole bunch of geometry and pinpoint exactly where you are. Now, imagine if those calculations were ambiguous. Your GPS might think you're here and also over there, a mile away, at the same time. Engineers who build these systems have to make absolutely sure they only get one single, unique solution.
And really, this quote just says it all. In engineering, in navigation, in physics, you have to know if the problem you're solving could have more than one right answer. Knowing how to find and deal with that ambiguity is an absolutely critical skill.
So, we'll leave you with this thought. The ambiguous case is a great reminder that sometimes the first, most obvious answer isn't the only one. You just have to know the rules so you can look a little closer. It makes you wonder what other problems, in math or just in life, might have a hidden second solution just waiting to be found.